Now, one of the things you should definitely be familiar with, and this is just a quick recap, are Newton's laws of motion. They are just given there. I'm not going to read them. You should be familiar with them. There's also even further details in the lecture notes if you need. But what we're really going to be using most of the time is Newton's law of gravitation, which you should all be familiar with as well. That depends on the two masses and the distance 1 over the distance squared and with the gravitational constant. Now, elliptical orbits are kind of fun and they're nice geometrically to understand what's going on. But if we are to make some predictions, if we ever want to send rockets or satellites, we should try to link geometrical considerations with physics. And we're not going to do it here in this module. If you actually want to go to the steps, I would recommend you going to one of the recommended books. That's Carroll and Osley, where they derive essentially an expression that links the position of the source with the angular momentum and the product of the masses. And there are still some geometrical considerations. And I assume you're all familiar with what angular momentum is, and also some of the things, even if I don't mention, it is important that angular momentum will depend on sine phi, but because we're dealing with gravity, it is a central force, and phi is always going to be 90 degrees or pi over 2. And this means that we're always going to be using mvr as angular momentum, and I'll not be bothered in keeping the phi's, just so that you understand and that it's perfectly clear. The reason why this expression is so useful is because we can link them with the other expression that we derived, which has no physics, but rather just describes things in terms of the ellipse and polar coordinates, such as theta and r. The great thing is that these r's, this one over here and the one over here, are exactly the same. And therefore, we can equal the expressions to actually find something incredibly useful. So you can write it as this. That gives you a relation between just the geometry on the left and physics on the right. Or you can write an expression for the angular momentum in terms of both physics and the properties of the orbit. And this is incredibly useful and powerful to extract physical information from the geometry of the orbits, or to extract geometry from physical information of an orbit. Now, before, we've actually looked and derived simple expressions to calculate the furthest distance from, for example, the sun, and the closest distance. So we looked at the perihelion, which is the closest, and the aphelion, which is the furthest. And with our new knowledge that goes beyond just getting some geometrical considerations, but that it actually allows us to write angular momentum in terms of physical properties, what we can do is, and again, this is just a reminder, because we're dealing with gravity, it is a central force, always points downwards, essentially at 90 degrees to the velocity, then we can very easily derive an expression. Now, at this point, we know what the radius is, and I've actually subbed it in here. The radius, or the distance at perihelion, is given as a times 1 minus e, which allows us to use the knowledge we just covered before and actually rearrange the expression to derive what is the velocity at the instant where an asteroid or a planet or anything else is orbiting the mass big M. And I think the only thing to note is everything that we did so far assumes this mass to be big when compared to the small mass m. That is the assumption, and if you look at the textbook where derivation is, that will be made very clear. Again, we've used our knowledge that at the closest point, theta is 0, phi is always pi over 2 because gravity is a central force, and it means that we can calculate, this is essentially the highest velocity that a planet will have because it is the velocity at the closest point. With similar arguments, you can derive a velocity at the furthest point. This will be the slowest that a planet, an asteroid, or a spaceship that's in orbit will have. And the arguments are basically the same. The big difference is that you start with an expression for angular momentum at that point where you use the distance to that point. and you simply rearrange the expressions until you get your final answer. It is important to point out that if you're asked to calculate a specific velocity at these special points, you will be able to actually use these expressions. You don't have to derive them, although knowing how to derive them will actually be quite useful because you will know where these expressions came from. And if you do have questions, please just get in touch. In the lecture notes, you will see that there will be lots of examples throughout the sections, in addition to the ones at the end. In this case, this is a very simple example of how we can use our newly gained knowledge of special points to calculate the distance, for example, from the sun, and also to calculate the speeds at those locations. So we can start by doing this with the Earth's orbit. So the Earth is 1 AU away from the sun on average. We can actually convert that into kilometers like this. And I told you that the Earth's orbit is almost a circle. That's because the eccentricity is really close to zero. Not quite zero, but very close to it. And if we use the expressions that we saw before, we can very easily calculate the closest point to the sun. We're actually very near it. I think it's been last week that the sun went through periapsis, and aphelium or apoapsis distance is slightly larger, but not much in terms of percentage. And finally, we can also calculate the speeds at which the Earth will be moving at these two extreme points. And I told you we just passed perihelion, or the closest point. So we're moving at a velocity very close to 30.3 kilometers per second. But in about 3 months, we'll be moving at a velocity that's about 29.3 kilometers per second. And I hope that using these is something very simple, but most importantly, that you understand how we derived all these expressions. Perhaps something more interesting is to try to calculate this for other objects, not just the Earth. And that's quite an interesting object in orbit of the sun that's going through the orbit of Mars and Earth. It's a car, it's a sports car. It's the one featured here that actually has already concluded at least one orbit, and it passed really close to Mars. For those of you that are interested in actually trying to calculate these orbits, you're free to do it. In this example that you also find in the lecture notes, what we're trying to do is to actually calculate the eccentricity and the speeds at the closest point to the sun and the furthest point to the sun. And this is a very good example of how, by just having the furthest distance and the closest distance, you can actually do this. So how do you do this? Well, you also have examples and at the end of the section, but you can use your knowledge essentially of the relations between these two distances, A and the eccentricity. So you can actually relate the radius, the closest approach, and the furthest approach to the object you're looking at, in this case the sun, and the eccentricity of the orbit. And this allows you to directly derive an expression like this. If you want to see the steps, they are at the end of the section. This is one of the problems you are asked to do that already has the solutions. And it turns out that the eccentricity of this orbit is 0.256. So it's not as circular as all the other planets nearby. And what this also allows you to do is we've seen that A is essentially the average of the closest and the furthest point. It's a very simple way of calculating the average distance. And you get this just above 1 AU. And this, of course, reinforces the fact that this car with the Starman is orbiting something that gets really close to the orbit of Mars and then goes back to the orbit of the Earth. To get the speeds at the furthest point and the closest point, you do exactly the same as you did for the Earth, and you get velocities which are very close to those of the Earth, but the one closest to the sun is actually slightly larger. And you can check out both the worksheet and the final subsection of section 3, where you have further examples.